Far from Earth, farther than any human-made object has ever ventured, a tiny spacecraft drifts in the darkness between stars. It is quiet there. No sunlight to warm its metal skin. No planets to swing by. No moons to capture its lens. Just cold, silence, and an endless black ocean dotted with ancient starlight. The spacecraft is called Voyager 1. Launched from Cape Canaveral in 1977, it was never meant to travel this far, and yet, 47 years later, it floats more than 15 billion miles from home, still alive, still speaking to us, still listening. It sends a signal weaker than a refrigerator light bulb, yet our massive radio dishes on Earth can still hear it. A faint whisper from beyond the solar system. That whisper carries secrets no one expected, because Voyager 1, drifting alone in interstellar space, has found things that defy logic, things that shouldn't exist, yet do. As it passed into the great unknown beyond the sun's protective bubble, Voyager uncovered a world that feels more alien than anything we've ever encountered. And it did so with instruments built when cassette tapes were still new. Even more amazing, Voyager 2, its slower twin, follows close behind. Together, the Voyagers form a pair of mechanical messengers, writing humanity's first letters to the galaxy. But beyond their sensors and radio antennas, they carry something else too. Golden records, copper discs wrapped in aluminum, encoded with sounds and images from Earth. Greetings in 55 languages, the heartbeat of a mother, a child's laughter, waves crashing against a beach, music from back to Chuck Berry, all carried aboard a spacecraft smaller than a school bus, now further from Earth than the Sun is from Neptune. Voyager 1 has traveled so far that the Sun now looks like just another bright star behind it. It has no fuel left to steer, no planet left to fly past, and yet it coasts onward toward the constellation Ophiuchus, a journey that will take it 40,000 years to complete. No brakes, no destination, just forward. Still, it watches. Still, it listens. The spacecraft's sensors are old, radiation burned, power hungry, degraded. But they are patient. In 2012, Voyager 1 did something no spacecraft had ever done before. It left the solar system. But what does that mean? And what did it find out there? To understand the shock of Voyager's discoveries, you have to imagine space not as an empty void, but as a frontier. At the center is our star, the Sun, which emits a constant stream of charged particles called the solar wind. These particles flow outward in all directions, creating a vast bubble known as the heliosphere. Inside that bubble, the Sun rules. Outside it, the galaxy begins. Scientists had long predicted that the edge of this bubble, the heliopause, would be chaotic. A violent, swirling mix of solar and interstellar winds crashing into one another. A stormy border full of turbulence and magnetic shock waves. Voyager was expected to detect chaos. But that's not what happened. When Voyager 1 crossed the heliopause in August 2012, there was no storm, no shockwave, just silence. One moment, the sensors buzzed with solar particles. Next, they were gone. The cosmic rays of deep space suddenly surged in. The solar wind vanished. A boundary so clear, it was like walking through a curtain into another universe. This was the first of many surprises, because the region beyond the heliopause, once thought to be cold, quiet, and empty, turned out to be alive with strange phenomena. Plasma waves, interstellar winds, particles that shouldn't exist, even magnetic fields behaving in ways no one could explain. Voyager's ancient instruments, running on less computing power than a wristwatch, were recording data that would take years to fully understand. Scientists on Earth, watching this stream of numbers trickle back across billions of miles, felt like they were peering into a hidden chamber of the universe, a chamber never before opened. Even more remarkable, Voyager 1 is still sending data today. It has enough electrical power to keep just a few instruments running. Its thermoelectric generators, which convert heat from radioactive decay into electricity, grow weaker each year. One by one, its subsystems are going dark, but it still whispers. It still remembers. Every day, a signal from Voyager takes over 22 hours to reach Earth, traveling at the speed of light. And every day, engineers at NASA's Deep Space Network listen patiently to its heartbeat. This tiny machine, built by human hands, now moves through a region of space untouched by sunlight, shielded from solar wind, wandering among the stars. It is not fast. It travels at 38,000 miles per hour, a speed that would circle Earth in less than an hour, yet it will take tens of thousands of years to reach even the nearest star. Yet for all its slowness, for all its silence, Voyager 1 has become a time traveler. Not only does it show us where we came from, it hints at where we're going, and perhaps, if someone or something ever finds it, drifting across the galaxy, it will tell them who we were. It began with a shift, not a loud bang, not a flash of light, just a subtle, almost imperceptible change in Voyager 1's data. August 25th, 2012. The day it left the heliosphere and crossed into a realm no spacecraft had ever entered: interstellar space. You might imagine the edge of the solar system as a clear line, a wall dividing our star's domain from the larger galaxy. But it's not quite so clean. Instead, it's more like walking through an invisible fog, thin in places, dense in others, gradually fading from the familiar warmth of the sun into the icy breath of deep space. This fog is the solar wind, a constant flow of charged particles blasting out from the sun at hundreds of kilometers per second. For more than 3 decades, Voyager had surfed that solar wind. But in August of that year, the stream stopped. Voyager's particle detectors, still functioning after 35 years, recorded something extraordinary. The density of solar particles dropped sharply, and at the same time, the number of galactic cosmic rays suddenly spiked. Cosmic rays, high-energy particles from exploding stars far across the galaxy, normally get pushed back by the sun's wind. But when Voyager slipped past the edge, the solar shield was gone. The spacecraft was now fully exposed to interstellar radiation. This moment marked humanity's first direct touch with the space between stars. The boundary it crossed is called the heliopause, the place where the solar wind's outward pressure is exactly balanced by the inward pressure of the interstellar medium. For decades, this edge was a theory, a math problem, a mystery. No probe had ever reached it, and when Voyager did, scientists weren't even sure at first. They debated, they argued, they waited for more data. That data came slowly, trickling in over months, like breadcrumbs from the edge of the galaxy. One of the clearest signals came from an unexpected source, the cosmic ray detector. As Voyager left the heliosphere, this instrument noticed that the high-energy particles from deep space were no longer being pushed away. They were flooding in. It was as though a cosmic dam had broken. The change was dramatic and sudden. The count of galactic particles doubled, then tripled. No longer sheltered by the sun, Voyager now felt the true bite of interstellar space. But there was something even more telling: a shift in plasma density. Now, Voyager's plasma detector had long since failed. It stopped working decades earlier. But NASA engineers, being eternally clever, found another way. They used the spacecraft's plasma wave instrument, essentially a radio receiver tuned to the natural vibrations of space. When a burst of solar activity sent a shockwave all the way out to Voyager, it stirred the local plasma. Those waves rippled through the medium like a tuning fork through water. By measuring the pitch of those plasma vibrations, scientists could determine how dense the surrounding space was. And what they found stunned them. The density was much higher than expected, 40 times greater than the solar wind. That confirmed it. Voyager wasn't just in a strange part of the solar system. It had exited entirely. It had entered the galaxy proper. Think about that for a moment. A spacecraft launched during the Cold War, powered by nuclear decay, controlled by 1970s technology. It had finally pushed past the sun's breath and into the true void. But it wasn't empty out there. Beyond the heliopause, Voyager encountered a region filled with strange pressure systems. Silence is
space
rare.
weather patterns shaped
Even
by
in a
magnetic
remote forest
fields,
and ion
there's the
flows
rustle
no
of
one
leaves,
had ever measured before.
the buzz of insects,
the sun's magnetic field,
whisper of wind.
once dominant, suddenly dropped away. In its place, a new magnetic field took over, one aligned not with our solar system, but with the broader spiral arm of the Milky Way galaxy. This was a whole new world. Cold, dark, ancient, and Voyager was alone in it. No other probe had been built to survive this long. Voyager 1 had endured cosmic radiation, freezing temperatures, and countless micrometeoroid impacts. Its instruments were aging, its power supply shrinking, and its computers were laughably outdated by modern standards. Yet it had done the impossible. And here's the strangest part. The crossing wasn't violent. There was no jolt, no crash, no major disturbance. Just a quiet transition from one realm to another. Like stepping from a warm pool into a colder one, only the sensors noticed the difference. That calmness was unexpected. Scientists had theorized for years that the heliopause would be turbulent, where the solar wind slammed into the galactic medium with chaotic force. But Voyager's data painted a gentler picture. There was pressure, yes. There were shifts and gradients, but no explosive boundary, no shredding shockwave, just a curtain, one made of invisible gas and magnetism, pulled back slowly by time. Voyager 1 had entered a realm untouched by sunlight, a place where the only warmth comes from the gentle hum of the galaxy's background radiation. A place no human has ever seen, yet one where our little probe now drifts, still carrying the golden record, still calling home. The crossing of the heliopause marked not just a scientific triumph, but a philosophical one. For the first time, we had sent something, anything, beyond our solar family, into the unknown, into the true vastness of the galaxy, and Voyager, silent and steady, kept moving forward. At first, it was simply too quiet. The moment Voyager 1 passed through the heliopause, its instruments began registering an eerie calm. Scientists expected turbulence, interference, some kind of boundary-crossing chaos. But instead, there was a sudden hush, so silent, so complete, that it felt unnatural. Voyager's particle detectors had been humming with solar activity for decades. Constant collisions with charged particles from the sun gave the spacecraft's instruments a kind of background noise, a static buzz of data. Then, in a single moment, that buzz went dead. Not because the spacecraft had shut down, not because the detectors had failed, but because the source of all that energy, the sun, was now behind it. This silence wasn't emptiness, though. It was something deeper, something more profound. It was the absence of our solar system's voice. But Voyager was now billions of miles from all that. Out here, sound cannot travel. There's no air, no medium to carry it. And electromagnetic chatter from the sun had all but disappeared. Yet Voyager's instruments were still listening, and what they heard, what they didn't hear, was as important as any discovery the spacecraft had ever made. Scientists had long believed the transition to interstellar space would be marked by chaos, plasma turbulence, magnetic reconnection, and swirling particle storms. But instead, the data revealed a shocking stillness. It was like emerging from a roaring crowd into an abandoned cathedral. No voices, no motion, just still air and shadows. Even stranger, the direction of the magnetic field didn't change the way they expected. You see, one of the key predictions about crossing into interstellar space was a noticeable shift in magnetic field orientation. Inside the heliosphere, the sun's magnetic field twists into a spiral pattern, shaped by the spinning of the sun itself. Outside, the galaxy's magnetic field was supposed to run in a completely different direction. But Voyager's magnetometer detected something else. The field was still there, stronger than expected, in fact, but it wasn't clearly different. It didn't twist, didn't flip, didn't fight back. It was as if the sun's field extended further than scientists imagined, or the interstellar field was somehow blending with it in ways no one had foreseen. And that quiet, that still, soundless darkness, it wasn't lifeless. In fact, Voyager's instruments soon picked up a faint ghostly music, ultra-low frequency plasma waves resonating through the interstellar medium. These weren't sounds in the way we hear them, but rather electromagnetic vibrations that Voyager's radio antenna could detect. NASA translated them into audible frequencies for human ears, long, drawn-out whistles, like wind brushing across a desert canyon. It was the sound of nothingness, singing. The plasma wave instrument, still active despite decades of wear, became Voyager's new ears in the void. Every few months, it would detect another rising tone, evidence of distant shock waves from the sun, still echoing across the border of interstellar space. Like a pebble dropped in a pond, solar eruptions continued to ripple outward long after Voyager had left their source behind. Each wave took more than a year to reach the spacecraft. Each was a reminder that, even out here in the galactic deep, the sun still had a voice, faint, slow, but present. But the silence between those waves was unnerving. In that silence, Voyager flew on, at nearly 11 miles per second, fast enough to cross the United States in 5 minutes, yet impossibly slow on cosmic scales. The stars ahead won't shift position for tens of thousands of years. The darkness won't brighten. The path will not change. That silence also presented a challenge for Earth scientists. Without dramatic data spikes or changes in direction, they had to examine Voyager's readings with exquisite care. A blip in radiation, a slight uptick in plasma density, a subtle shift in frequency. Any of these might reveal secrets about the invisible ocean between the stars. The Voyager team, now made up of new generations of scientists, combed through the data with reverence. These weren't just numbers, they were the whisperings of deep space itself. It was during one of these long silences that Voyager detected a rare and fascinating event. A plasma wave burst, a sudden increase in high-frequency waves unlike anything seen before. It suggested a nearby solar event had sent a powerful shockwave all the way across the heliopause. Voyager had heard the echo. It was as if deep space had spoken back. These discoveries changed our understanding of interstellar space entirely. No longer did scientists think of it as cold and dead. Instead, it was a dynamic place. Calm, yes, but filled with hidden currents and unseen pressures. The magnetic field wasn't chaotic, but ordered. The plasma wasn't still, but vibrating. The silence wasn't empty, but rich with potential. And Voyager 1, ancient and alone, was the only one who could hear it. Back on Earth, the distance had become almost impossible to fathom. The radio signals from Voyager took over 21 hours to arrive, each one traveling at the speed of light. And yet they came, day after day, carrying with them the hush of interstellar space. A silence so complete, so unearthly, it became a discovery in itself. Out beyond the edge of our solar system, Voyager 1 was drifting through silence. But silence doesn't mean stillness. Hidden within that quiet was something unexpected. The spacecraft's instruments began detecting waves, pulsing, trembling waves in the very fabric of space. But these were not sound waves, and they didn't come from stars or planets. They were plasma waves, ripples moving through charged particles in the interstellar medium. Now, plasma might sound exotic, but it's actually the most common state of matter in the universe. It's a sea of electrically charged gas found in stars, lightning bolts, and space itself. And Voyager, despite its age, had just found a whole new kind of plasma, one that shocked even the most seasoned astrophysicists. Inside the heliosphere, Voyager had grown used to the sun's plasma, fast-moving, hot, and constantly blowing outward as solar wind. But now, in the quiet sea of interstellar space, the plasma was cooler, denser, and more stable than expected. Scientists believed the region beyond the heliopause would be full of random fluctuations, a turbulent mess of galactic forces. Instead, what Voyager discovered was a smooth ocean of plasma that pulsed with calm, regular rhythms. The plasma wave instrument on board Voyager isn't like a camera or a microphone. It listens to space in frequencies well below the range of human hearing, electromagnetic tones generated by electrons oscillating in the interstellar medium. When Voyager crossed into this new region, those tones changed. They rose in pitch, grew louder. Something was different. One of the most surprising findings came in 2013, about a year after the heliopause crossing. A coronal mass ejection, an enormous explosion of solar particles from the sun, had made its way all the way to Voyager's new location. The ejection pushed a shockwave into the interstellar plasma. That's when Voyager recorded a sudden spike in plasma wave activity, a clear tone, like the ringing of a bell. NASA scientists converted that plasma vibration into sound and played it back on Earth. What came through was haunting. A rising note, like the eerie whistle of a flute in an empty cathedral. It lasted about 6 weeks. From this tone, scientists calculated that the surrounding plasma was nearly 40 times denser than what Voyager had encountered inside the heliosphere. That was astonishing. It told us, for the first time, what interstellar space was truly like. This wasn't the empty void of science fiction. This was a structured, pressurized region filled with invisible material, and Voyager was sailing through it like a boat on a dark cosmic sea. But it wasn't just the density that surprised researchers. It was the behavior of that plasma. Back when Voyager 1 was expected to cross into interstellar space, most theories predicted turbulence, violent mixing between the solar wind and galactic plasma. Instead, the boundary was smooth and the plasma waves were steady. This calmness baffled everyone. Why wasn't there more chaos? Had Voyager passed through the heliopause during a quiet phase of solar activity? Or was the boundary more orderly than we imagined? The answers weren't obvious, but the implications were massive. It suggested the interstellar medium was not some chaotic cloud, but a vast flowing system with rules of its own. Rules we were only just beginning to glimpse. Even more mysterious was how the plasma seemed to resonate in response to distant solar events. When the sun erupted, the shockwaves rippled outward for over a year, eventually reaching Voyager. These solar storms didn't stop at the edge of the heliosphere. They kept going, disturbing the plasma out in interstellar space like a distant thunderclap rolling across a calm lake. Each time a solar eruption reached Voyager, its plasma wave detector sang again. Each tone gave scientists new data about the density, temperature, and behavior of the space beyond our star's reach. And these measurements weren't just new, they were unprecedented. Before Voyager, everything we knew about interstellar space came from telescopes and models. We could only guess at what was out there. Voyager gave us measurements, real numbers from real instruments floating in the real galaxy. It was like the difference between looking at a mountain through binoculars and actually standing on its peak. And that data revealed something even more profound. Plasma, it turns out, doesn't just fill the space between stars. It might shape it. The density and movement of this charged gas influence how stars form, how magnetic fields evolve, and even how cosmic rays travel across the galaxy. Voyager's quiet drift through this medium was, in fact, helping scientists rewrite the story of how galaxies grow and change. Every spike in plasma wave activity brought new surprises. One signal in particular stood out. It suggested that Voyager had entered a more compressed region of interstellar space, a kind of denser cloudlet drifting through the larger galactic neighborhood. These clouds, invisible to telescopes, had been theorized for decades. Now, Voyager was floating through one, and inside this denser region, something changed again. Plasma densities rose, magnetic fields strengthened. Voyager's instruments recorded the new environment with calm regularity. No panic, no drama, just steady transmission from the oldest traveler humanity has ever sent. Even as its power supply dwindles, Voyager continues to record these plasma waves, each one a ghostly signal from an ocean so vast it defies comprehension. Out there, in the darkness between the stars, Voyager drifts through a sea of invisible pressure, carried by forces older than our planet. And in that sea, it has become more than a spacecraft. It has become a listener, a lone ear tuned to the heartbeat of the galaxy. When Voyager 1 left the heliosphere behind, it stepped into a place where few expected anything at all. Scientists had predicted a gradual drop-off in solar activity, a thinning of particles, perhaps a quiet hum from the distant galaxy. But as the spacecraft moved further into interstellar space, something entirely different emerged, a sharp and unexpected rise in cosmic rays. These weren't just random particles, they were high-energy bullets, flung across the galaxy by violent events, exploding stars, neutron star collisions, and maybe even the chaotic maelstroms near black holes. Voyager's radiation detectors, still faithfully reporting data after decades of travel, began to register a dramatic increase in these galactic intruders. Inside the heliosphere, cosmic rays are filtered and softened by the solar wind. The sun's magnetic field and its steady stream of particles create a kind of shield, a cosmic umbrella that blocks the most dangerous radiation from getting close to the inner planets. That's one reason Earth is so hospitable to life. But the farther Voyager traveled, the weaker that protective shield became, until finally it vanished. Beyond the heliopause, there is no more solar wind to block the incoming rays, and as Voyager crossed that invisible line, cosmic radiation surged, like stepping out from the shade into a sudden downpour. The intensity of cosmic rays beyond the heliosphere shocked scientists. The increase wasn't gradual, it was immediate, sharp, and persistent. The detector aboard Voyager 1 saw levels of radiation that were far higher than anything it had measured before, and those levels stayed high. But what exactly are cosmic rays? They're not rays at all, but particles, mostly protons, with some electrons and atomic nuclei thrown in, and they travel at near light speed, accelerated by some of the most energetic processes in the universe. Many originate from supernova explosions, where dying stars collapse and hurl their outer layers into space with unimaginable force. These events scatter atomic shrapnel across the galaxy, and Voyager was now floating in the middle of it. Some cosmic rays carry energy so intense they can pass straight through spacecraft, and even through people. On Earth, our atmosphere and magnetic field protect us from the worst of them. But in deep space, Voyager was exposed, fully and continuously. This flood of cosmic radiation had both scientific and philosophical implications. First, it told researchers exactly where the spacecraft was. The sudden increase in cosmic rays confirmed Voyager had entered a new region, one that was no longer dominated by the Sun, but by the galaxy itself. It was one of the clearest pieces of evidence that the probe had truly crossed into interstellar space. Second, it offered scientists a priceless opportunity to study galactic radiation directly, to measure its energy, its intensity, and its interaction with the interstellar medium. No other probe had ever done this. Everything we knew before came from indirect observation, from detectors on Earth or in orbit, filtered by the Sun's influence. Voyager, drifting silently beyond that filter, became our first outpost in raw galactic space. But there was a third, more chilling realization. If a human were aboard Voyager 1, unshielded and exposed, they would receive a lethal dose of radiation in mere months. It was a stark reminder that deep space is not friendly to life as we know it. The same particles that offered a goldmine of data were also a constant, invisible threat. Even spacecraft electronics aren't immune. Over time, high-energy particles can fry circuits, corrupt memory, and degrade sensors. Voyager was built tough, but every year it survived beyond the heliopause was a victory against cosmic decay. The rising tide of radiation was like a slow, creeping pressure, grinding down the probe's aging systems one bit at a time. But Voyager, resilient and silent, continued to transmit. The data revealed something else too. The cosmic rays weren't just high in energy, they were remarkably uniform. Unlike the solar particles inside the heliosphere, which fluctuate wildly depending on solar activity, these galactic particles formed a smooth, steady background. It was as if the spacecraft had entered a room filled with quiet, powerful music, always present, always humming in the background. Yet even in that smoothness, there were surprises. Voyager occasionally detected brief dips and surges in radiation, signs that something was happening nearby. Perhaps a passing shockwave from a supernova. Perhaps an interaction with a dense pocket of interstellar gas. Each fluctuation offered a new mystery to solve, a new page in the cosmic story unfolding far from Earth. And so, Voyager's detectors kept counting, one particle at a time, like a Geiger counter ticking in a haunted house. Except the house was the galaxy, and the ghosts were ancient explosions from millions of light years away. Every tick was a whisper from the past. These whispers taught us something deeply humbling, that our solar system is a gentle cradle in a much harsher galaxy. We live inside a protective bubble blown by our star, safe from most of the cosmic radiation that roams the universe. But outside that bubble, the truth is stark. Space is not silent. It is radiant, saturated with the residue of ancient cataclysms. And Voyager, ancient and enduring, is still flying through it, still counting, still listening. In doing so, it reminds us just how thin our protective walls really are, and how far we've come, sending a fragile machine into the galaxy's glowing tide. The longer Voyager 1 drifted through interstellar space, the more it revealed a strange and subtle truth. The galaxy has texture, not physical bumps and grooves like sandpaper or bark, but invisible layers, patches of dense gas, waves of magnetic fields, zones where charged particles thickened or thinned. The spacecraft, blind in a human sense, but exquisitely sensitive to electromagnetic forces and plasma density, became like a fingertip tracing the grain of something vast and ancient. One of the first signs of this texture came not from Voyager's eyes, there are no cameras running anymore, but from its plasma wave instrument. As the spacecraft moved deeper, it detected tiny, high-pitched vibrations, faint tremors that translated into tones, much like notes on a piano. Each note represents a different density of plasma, the charged gas that fills space between stars, and the song was changing. The farther Voyager traveled, the higher those tones became, like the rising wail of a siren in the distance. It wasn't that the spacecraft was speeding up, it was that the plasma around it was getting denser. This surprised scientists. They had assumed that interstellar space would be mostly empty, thin, cold, and silent. But Voyager showed that this region wasn't flat or uniform. It had layers, ridges, ripples. Imagine sailing across a dark ocean and discovering not just waves, but entire underwater mountains, rising and falling invisibly beneath the surface. So where did this plasma come from? Most of it originated from stars, especially from supernovae. When massive stars explode, they eject shells of gas into space. Over time, those shells drift and spread, forming large, cloud-like structures. Some are dense and cold, others are hot and diffuse. Voyager had entered one such region, a place where the interstellar medium, for reasons still not fully understood, had grown denser than expected. In fact, the plasma density near Voyager reached more than 40 times what it had been just beyond the heliopause. That's still incredibly thin by Earth standards, thinner than the best vacuum we can create in laboratories. But in space, it was like hitting a fog bank after miles of clear air. And this fog could speak. Not in words, of course, but in those plasma waves, scientists could hear the faint echoes of faraway storms, like seismic tremors traveling through deep rock. Solar events that happened years earlier, eruptions on the sun, coronal mass ejections, had created shock waves that eventually reached Voyager, compressing the plasma and raising its pitch. Voyager was recording those effects in real time, allowing us to study how solar energy ripples outward long after it seems to disappear. Each tremor, each wave, each subtle shift told a story, but it also raised new questions. Why was the plasma so dense here? Was Voyager entering a filament, one of the thin, thread-like structures that stretch between stars? Was it brushing the edge of an ancient supernova remnant? Or was this just a normal patch of galactic space that we'd never had the tools to examine before? For the Voyager team, every change in data was a breadcrumb. They followed these clues carefully, day after day, measuring the slow rise and fall of plasma frequency, the shifting tone of the interstellar wind, the subtle bumps in magnetic pressure. Voyager had become our deep space weather station, reading the temperature, pressure, and humidity of a place no human would ever see. And it wasn't just passive observation. In 2020, a solar flare that had occurred 14 months earlier finally reached Voyager. The wave of energy slammed into the local plasma, compressing it and briefly boosting its density even more. The spacecraft recorded the entire event. For scientists back on Earth, it was like hearing a distant thunderclap from a storm that had already passed long ago. These time delays became part of the puzzle. Events on the Sun take hours to reach Earth, days to reach the outer planets, and over a year to catch up with Voyager 1. In a way, the spacecraft was listening to a cosmic echo chamber, hearing the past replayed across billions of miles. That's when another mystery emerged. the magnetic field readings continued to defy expectations. Even though Voyager was far beyond the Sun's direct influence, the magnetic field it detected still seemed aligned with the solar system's original field. Why? One theory suggests that the heliosphere itself is dragging part of the Sun's magnetic field along with it, like a jellyfish trailing tendrils into the ocean. Another idea is that the local galactic field has been bent or twisted by interactions with the solar wind, creating a kind of transitional zone, one that stretches much farther than scientists thought. Whatever the cause, the result was clear. Voyager was not moving through a clean, empty vacuum. It was navigating a tangled, shifting sea of invisible forces, and it wasn't done yet. As of now, Voyager 1 continues to inch forward, roughly 3.6 AU, about 335 million miles, farther each year. It moves silently, steadily, and alone. No camera films the journey. No light shines ahead. Yet every few days, its instruments send back whispers, a pulse of plasma, a magnetic twist, a faint rise in radiation. Each signal is a gift from a region of space no other spacecraft has touched. Each is a letter from the edge of forever. And each one adds a stroke to the ever-growing portrait of the Milky Way. Not as a distant spiral seen through a telescope, but as a living, breathing ocean of particles and waves and magnetic tides. Voyager is not just a machine anymore. It is our first explorer in the interstellar deep, feeling its way forward in the dark, mapping the invisible textures of a galaxy we barely understand. Voyager 2 follows. While Voyager 1 had already made history by becoming the first human-made object to enter interstellar space in 2012, the story didn't end there. 6 years later, its twin, Voyager 2, would follow, not along the same path, but through a different region of the heliosphere. And what it found was startling. On November 5th, 2018, Voyager 2 crossed the heliopause, the invisible boundary where the Sun's solar wind gives way to the interstellar medium. The spacecraft had been launched 16 days before Voyager 1 back in 1977, but its trajectory was slower and more complex, weaving past Jupiter, Saturn, Uranus, and Neptune. Unlike Voyager 1, which took a more direct route upward and out of the plane of the planets, Voyager 2 veered south, angled below the solar system. This different path would soon reveal something astonishing. The edge of the solar system isn't the same everywhere. For years, scientists assumed the heliopause would be roughly spherical, a neat, even boundary surrounding the Sun's influence. But Voyager 2 crossed into interstellar space at a different distance than Voyager 1 had. And not just a little different, by over 1.5 billion kilometers, or nearly 10 times the distance between Earth and the Sun. Imagine standing inside a giant, invisible bubble. Voyager 1 punched through the top. Voyager 2 escaped through the bottom. And the bubble wasn't symmetrical. It was warped, squashed, and possibly even tilted. This was one of the first signs that the heliosphere, the Sun's vast protective shield, was not the smooth, even shell we had pictured. Instead, it was shaped by external forces, pressure from the surrounding interstellar medium, magnetic fields, and even shockwaves from ancient supernova. But it wasn't just the boundary shape that differed. As Voyager 2 crossed the heliopause, its sensors remained active in ways Voyager 1's had not. That's because Voyager 2 still had a functioning plasma instrument, whereas Voyager 1's had failed years earlier. This gave scientists their first direct measurements of how plasma behaves at the solar system's edge, and what they found was surprising. As the spacecraft pierced through the boundary, it recorded a sharp increase in plasma density, just like Voyager 1 had hinted at. But the increase happened much faster and more suddenly. Within a single day, Voyager 2 passed from the low-density solar wind into plasma that was nearly 20 times denser. It was as if the spacecraft had driven through a thin fog and instantly hit a wall of thick smoke. Even more puzzling, the magnetic field direction did not shift dramatically, just like with Voyager 1. This contradicted predictions. Scientists had expected a clear difference in the direction of magnetic fields inside versus outside the heliosphere, but instead, both Voyagers reported magnetic fields that were still oddly aligned. Were the interstellar magnetic fields twisted? Were the spacecraft somehow still inside a transitional zone, even after crossing the heliopause? This mystery deepened with Voyager 2's data, because its magnetometer worked better than Voyager 1's at that stage. And yet, both readings agreed. The field outside looked surprisingly similar to the one inside. One possibility, that the Sun's magnetic field reaches farther than we thought, wrapping itself around the solar system like a loose, stretched-out blanket. Another theory suggests that the interstellar magnetic field is simply aligned in a similar direction to the Sun's in this region of space. A cosmic coincidence, but not impossible. But Voyager 2 had more to say. It detected waves and shocks, disturbances in the plasma that hinted at events far beyond the heliopause. For instance, when the Sun belched out a large coronal mass ejection, Voyager 2 could detect the faint ripple long after it had passed Earth and the outer planets. This gave scientists a rare opportunity to watch how solar activity propagates across unimaginable distances. It's a bit like throwing a stone in a lake and seeing ripples hit a far-off shore years later, and there was something poetic in the fact that both spacecraft were now exploring interstellar space in stereo, like two ears in the dark, listening to the same symphony from different corners of the room. With two data points, scientists could begin to construct a more complete picture of the heliosphere's true shape. It wasn't a sphere. It wasn't even a teardrop. It was something far more organic, shaped by invisible currents and ancient winds, by the tug of galactic fields and the Sun's aging breath. Even more thrilling, Voyager 2's instruments were in better condition than Voyager 1's. It had more tools still working: plasma sensors, cosmic ray detectors, a healthy magnetometer. This made Voyager 2 our most capable deep space observatory beyond the Sun's reach. Its observations confirmed that the galactic cosmic rays, high-energy particles from beyond our solar system, were much more intense beyond the heliopause. Inside the solar bubble, the Sun's magnetic field helps shield us from these dangerous rays. But outside, it's a storm of radiation. Voyager 2 was soaking in that storm, measuring the flux, recording the rhythm. And in doing so, it helped us understand something vital: how Earth is protected. Without the heliosphere, our planet would be bombarded by this high-energy radiation. Life as we know it might never have emerged. The solar system's invisible shield, a force field made of wind and magnetism, had shaped the very conditions for life to exist. And now, for the first time in history, we were studying the boundary of that shield from both above and below. From the eyes of two ancient machines, humming and clicking in the dark, still loyal after 4 decades. So much of space exploration is about movement: launches, orbits, landings, impacts. But Voyager's journey is about stillness. It doesn't steer, it doesn't turn, it simply drifts and listens. And as Voyager 2 sailed silently beyond the Sun's frontier, it whispered truths not just about space, but about our place inside it. A puzzling asymmetry. The solar system, as you've always seen it in science books or classroom posters, is usually shown as a neat collection of planets orbiting in perfect rings around the Sun. maybe even floating inside a giant, clear bubble. But Voyager 1 and 2 have now told us something strange and unexpected. The bubble isn't a bubble at all. In fact, it might not even be round. Back on Earth, scientists had long imagined the heliosphere, that vast protective zone around the Sun, as a sphere or, at most, a teardrop. The idea was simple. The solar wind pushes outward in all directions, and eventually, the pressure of the interstellar medium pushes back, forming a clear boundary. That boundary is the heliopause. But the Voyager twins painted a very different picture. Let's rewind. Voyager 1 exited the heliosphere in 2012 at a distance of 121.6 astronomical units, AU, from the Sun, where 1 AU is the distance between Earth and the Sun. Voyager 2, on the other hand, exited in 2018 at about 119 AU. That may not seem like a big difference, just under 3 AU, but in the grand design of the solar system, that's a massive lopsidedness. It's the difference between one side of a bubble stretching 300 million kilometers farther than the other. And remember, the Voyagers didn't leave in the same direction. One went north of the solar system's plane, and one went south. This asymmetry shook up everything we thought we knew. Imagine you're blowing a balloon, but instead of inflating into a perfect circle, it stretches oddly in one direction, slumps in another, and even gets pinched at certain points. That's our heliosphere, an irregular, wrinkled, distorted balloon drifting through the galaxy. Why is this happening? Well, it turns out that the interstellar medium, the space between the stars, isn't as empty or gentle as we thought. It's filled with magnetic fields, plasma waves, and particles left behind by long-dead stars and ancient supernovae. These galactic forces are constantly pressing against our solar system from the outside, like invisible weather. One strong suspect in this cosmic tug-of-war is the local interstellar magnetic field. Unlike the Sun's magnetic field, which curves and bends with the solar wind, the galactic magnetic field is relatively straight and strong. As it presses against the heliosphere, it likely squeezes and flattens one side more than the other, explaining why Voyager 2 exited at a closer distance. But that's not all. Another wrinkle in the story came from Voyager 1's and Voyager 2's magnetic field readings. You see, scientists expected a major shift in the direction of the magnetic field once the spacecraft crossed the heliopause, from the Sun's spiraling field to the galactic one. But both spacecraft recorded only slight changes, and strangely, the two measurements didn't match each other. The field Voyager 1 detected was tilted at a certain angle. Voyager 2's field was tilted at a slightly different angle, almost as if they were sampling the same room from two different corners, and each corner had its own unique draft of wind. This deepened the mystery. Were the Voyagers still inside a kind of magnetic transition zone? Was the heliopause not a hard boundary, but a thick, fuzzy border that shifts with time? Or perhaps the heliosphere was being compressed and dragged like a jellyfish in a current, its tentacles trailing in some directions while the head is pushed back. Computer models scrambled to keep up. New simulations now show a heliosphere that looks comet-like, with a blunt leading edge facing the galactic wind and a long flowing tail behind. But even this image is debated. Some researchers suggest the Sun's magnetic field could be forming a bubble within a bubble, with layers of interacting winds and fields shaped like petals on a flower. And that's where Voyager gave us something priceless: truth from beyond the textbook. For decades, scientists could only guess at what the edge of the solar system looked like. They built simulations, studied solar storms, and watched cosmic rays from afar. But the Voyagers were the first to touch that edge, to cross it, to feel it. and to send back data we could trust, even if we couldn't fully explain it. The data also helped scientists understand the shape of our sun's influence, not just where it ends, but how it moves through space. You see, our entire solar system is not standing still. It's flying through the galaxy at nearly 828,000 kilometers per hour, carrying the sun and all its planets like a ship sailing through a cosmic sea. As it moves, the heliosphere changes shape, stretching, rippling, even shuddering with solar storms. And every change affects how well it protects us from cosmic radiation. Think of the heliosphere as Earth's first line of defense. The more we understand its shape, the better we understand how Earth has remained shielded from the worst of the galaxy's storms. And what Voyager gave us was not just knowledge, but something more profound: perspective. For centuries, we imagined our solar system as the whole of the universe. Then we realized we lived in a galaxy. Then we realized there were billions of galaxies. Now, with Voyager's help, we've stepped outside the solar system and looked back at it, not from afar, but from beyond. And what did we find? That the edge is soft, that the shape is lopsided, that the boundaries between us and out there are far more tangled than we thought. In a way, the Voyagers are like bottles tossed into a vast ocean, not meant to return, but still carrying messages. And with each passing year, as they drift farther into the void, they tell us not just about where we've been, but how strange and beautiful it is to leave home. Sounds from the void. You might think that space is silent, utterly, eternally silent. After all, there's no air, no wind, no bird song, no rustling leaves. But Voyager taught us something strange. Space can sing, and out beyond the planets, past the warm breath of the sun, those songs become haunting. Let's step into the quiet. When Voyager 1 crossed into interstellar space, scientists weren't sure what it would encounter. Would there be radiation storms, a drop in solar particles, a sudden shift in magnetic fields? Some of those happened, yes. But something else did too. Something eerie. The spacecraft picked up a sound, not a sound like we hear with our ears. Remember, space is a vacuum. There's no air to carry traditional sound waves. But Voyager was equipped with a plasma wave instrument, a sensor designed to detect oscillations, tiny ripples, in the charged particles floating around in space. And those ripples could be translated into audible frequencies. That's when NASA heard it. A rising tone, a ghostly whistle, like a siren made of starlight. It came from the plasma, the sea of ionized gas that exists between the stars. Out in interstellar space, plasma density is higher than inside the solar bubble. And when Voyager 1 passed through it, that difference became music. Scientists took those plasma wave signals and converted them into sound. The result? A slow, otherworldly wail, soft, rising, echoing, like a chorus of glass instruments in the distance. It's not quite music, not quite noisy, but it's alive. You can listen to it. It's real. Voyager's message is no longer just data or digits. It's a song from outside the sun's domain. And here's what's even more fascinating. Those plasma waves don't just happen on their own. Sometimes they come in bursts, sharp, rising tones, like flares from the dark. And those flares often happen after solar storms. The sun sends out massive bursts of energy called coronal mass ejections. These storms travel through the solar system like waves through water. Even after the Voyagers had passed the heliopause, even after they were out in interstellar space, they still felt those waves. Months or even years after a solar eruption, Voyager's instruments would pick up a plasma wave burst, as if a ripple from the sun had finally caught up with it. Imagine that. The sun roared in 2012, and Voyager heard the echo in 2014. These plasma songs help scientists measure the density of interstellar space. You see, the higher the pitch of the plasma waves, the denser the plasma. Voyager 1 recorded several such events, and each one revealed new details about the interstellar medium. And Voyager 2? It heard them too. Even before it crossed the heliopause in 2018, Voyager 2 began detecting similar plasma waves. After its crossing, it too sang back the chorus of the stars, another lonely tune from the edge of everything. What do these eerie sounds tell us? They tell us that space is not dead, that far from being an empty void, the space between stars is alive with energy, that even the dark has structure, that even silence has rhythm. They also tell us something deeply human, because when we convert those signals to sound, we give ourselves a way to feel space, to experience it, not as charts and graphs, but as something that stirs the imagination. You don't need a physics degree to hear Voyager's song. You just need ears and wonder, and that's the thing. These spacecraft, drifting so far from home, still communicate with us in a way we can understand. They send pulses of data through the deep space network, but inside that data is emotion. Inside that data is music. You can picture it now. Voyager 1, gliding through a windless sea of stars, its instruments still whispering, still listening. Its long antenna tilted back toward Earth, catching a tiny sliver of sunlight as it coasts farther and farther away. And in the silence, it hears a ripple, a vibration, a voice in the dark, the voice of the galaxy. And just for a moment, Earth listens back. We may never reach those stars, not in our lifetimes. But Voyager did. It reached them, and it heard them, and it let them sing through us. And what do those songs say? They say, "You are not alone." They say, "The universe is still speaking." And they say, "You left a footprint, even in the stars." The infinite echo. By now you may be wondering, how can something so far away still speak? After all, Voyager 1 is more than 15 billion miles from Earth. Light from the sun takes over 22 hours just to reach it. A signal from Earth takes just as long to get there, and the same to return. That means every time NASA sends a message, they wait nearly 2 full days to hear back. It's like talking to someone on another continent who only replies once every 2 sunsets. And yet, it works. How? The secret lies in something that Voyager carries like a heartbeat, its radio signal. A soft whisper of energy, powered by a decaying plutonium battery, beamed across the void using a 3.7 meter, 12-foot dish antenna. That signal is incredibly weak by the time it reaches Earth, billions of times fainter than a digital wristwatch's radio waves. In fact, Voyager's signal is so faint, it's equivalent to a 20-watt light bulb shining all the way from interstellar space, and Earth still hears it. Thanks to the Deep Space Network, a global system of giant antennas located in California, Spain, and Australia, we can catch Voyager's whispers. Each station has 70-meter-wide dishes that can pick up the faintest of messages. These dishes don't just listen once, they track Voyager every single day, sometimes for up to 11 hours at a time. Through this quiet connection, Voyager continues to send us measurements, plasma densities, magnetic fields, cosmic ray levels. Each piece of data is like a postcard from a place no one's ever been. And that postcard comes with a ticking clock. You see, Voyager's power supply is fading. It uses something called an RTG, a radioisotope thermoelectric generator that turns heat from decaying plutonium into electricity. But after nearly 50 years, that power is dwindling. Each year, Voyager loses about 4 watts. Slowly but surely, systems have been shut down. Heaters, cameras, instruments, all turned off to save power for the few core sensors that still matter. NASA's goal? Keep at least one working science instrument running as long as possible, ideally until 2026 or 2027. After that, there won't be enough power to continue. The spacecraft will go silent. But even then, Voyager won't stop moving. Without power, it won't be able to talk, but it will still drift, quietly, eternally, into the interstellar dark, carried not by engine or wind, but by inertia, obeying the laws of gravity and momentum. A message in a bottle floating through a cosmic sea. And that brings us to the real echo. Because Voyager isn't just sending data, it's carrying a message for others. Affixed to the side of both Voyager 1 and Voyager 2 is something bold, strange, and deeply human. The Golden Record. You might have heard of it. It's a 12-inch gold-plated copper disc, and on that disc is a library, a time capsule, a portrait of Earth, sounds of whales, birdsong, a kiss, a heartbeat, greetings in 55 languages, music from Beethoven, Blind Willie Johnson, and a Navajo night chant, and pictures of Earth's people, landscapes, DNA, even a woman licking an ice cream cone. Why? Because Voyager might last billions of years. Long after our cities crumble, long after the continents shift, long after the sun swells and dies, long after we are gone. And if someone or something ever finds it, they'll find a voice, a record of who we were. Astronomer Carl Sagan helped design the record. He said, "The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space." But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. It does. It says that we were curious, that we dreamed, that even in our tiny corner of the galaxy, we dared to speak to forever. Think about that. Out there, in the darkness beyond stars, there's a golden disk floating endlessly, our echo, waiting to be heard. And even if no one finds it, even if the record drifts untouched forever, it still matters. Because we made it. We sent it. We dared to believe that someone else might care. So when Voyager falls silent, it won't be a death. It'll be a transition. From mission to monument. From communication to legacy. It will become a part of the galaxy now, forever. A quiet traveler, a silent ambassador, a tiny craft with a golden heart, sailing endlessly through interstellar tides. And somewhere, far behind it, on a pale blue dot drifting around an ordinary star, someone will still be listening. Because Voyager's echo doesn't end with the silence. It lives on in every scientist who studies its data, in every child who hears its song from the stars, in every dreamer who wonders what might be out there. It lives on. In you. The first stars Voyager will meet in 40,000 years. By now, you know that Voyager 1 has left the solar system. You know that it sails through the interstellar deep. And you know that it carries a message to the stars. But where is it going? What happens to a spacecraft that no longer belongs to any star, any planet, any sun? Let's follow it, forward in time. If nothing interferes with Voyager 1, no collision, no gravitational capture, it will continue to coast through the galaxy, slowly but surely heading in the direction of the constellation Ophiuchus. More specifically, It's on a long, quiet path toward a star system called Gliese 445. That's a red dwarf star about 17.6 light years away. But here's the twist. Voyager isn't aiming for it like a spaceship in a science fiction movie. It's not navigating. It's drifting, slowly, passively, carried only by the momentum it had when it left Earth. And because both Voyager and Gliese 445 are moving, their eventual meeting is not exactly close. But in about 40,000 years, Voyager 1 will pass within 1.6 light years of Gliese 445. That's far, much farther than the distance between the Earth and the nearest star, Proxima Centauri. But in cosmic terms, that's practically a handshake. Let that number settle in. 40,000 years. That's more than 6 times the entire span of recorded human history, longer than the time since the Ice Age. By the time Voyager 1 brushes near Gliese 445, Earth will be, well, we can't even guess. We might be gone, we might be gods, we might be dust, but Voyager will still be going. And that's not all. In about 296,000 years, Voyager 2 will pass close to another star, Ross 248, another red dwarf. It'll get even closer, about 1.7 light years. That might not sound impressive until you remember, nothing built by humans has ever gone farther, and yet, that's still nowhere near another planet. These encounters won't be close enough for the Voyagers to be captured by the star's gravity. They won't orbit. They won't land, they won't explore, they'll just keep going, passing star after star, century after century, for millions, maybe billions of years. Eventually, they'll circle the Milky Way galaxy. Yes, circle the galaxy. It takes our solar system about 225–250 million years to make one orbit around the galactic center. Scientists believe that both Voyagers will continue drifting through that spiral path, caught in the gentle whirl of the Milky Way. They'll complete multiple galactic orbits over time, outliving not just civilizations, but entire eras. Even as the stars themselves change, forming, exploding, dying, the Voyagers will drift, untouched. Their metal surfaces might corrode. Cosmic radiation might pockmark their skin, but their basic structure, it could last for eons. And the golden record, it's made of gold-plated copper, carefully encased in an aluminum cover, etched with instructions, how to play it, where we come from, and how to decode its sounds and images. It's been engineered to survive the harshest environments. And if no catastrophic collisions occur, the record could last 1 billion years or more. That means it could outlast Earth itself. Yes, really. In about 5 billion years, the Sun will swell into a red giant, swallowing Mercury and Venus, and possibly even Earth. Our oceans will boil, our mountains will melt, our history might vanish, unless we've found a way to move beyond this planet. But Voyager will still be out there, drifting, gliding, carrying a frozen time capsule of Earth across the cold black. Isn't that wild? That's something we made with our hands in the 1970s, before smartphones, before the internet, before most of today's population was even born. Could one day be the last trace of humanity. If intelligent beings ever find it, what will they think? Will they play the sounds of our laughter and songs? Will they see the photos of our landscapes, our animals, our DNA, our buildings? Will they wonder what happened to us? And even if they don't, even if no one ever finds the record, the fact that we sent it still matters, because it shows something beautiful, that we looked up, that we wondered, that we weren't afraid to be small, but to act big, that we were a species that reached into the dark and left a message, just in case someone might one day listen. So as Voyager 1 flies past Gliese 445 and Voyager 2 coasts near Ross 248, and the galaxy slowly turns beneath them, remember, you live in the era that built them. You are a part of the only species, so far, that has touched the stars. And even when Earth is quiet, your voice will still echo through machines older than memory, in a song longer than time. Goodbye, but not silent. When Voyager stops talking, now we come to a quieter part of the story, one that is both expected and heartbreaking. Because someday, sooner than we'd like, Voyager will stop talking to us. Not because it's broken, not because it's lost, but because it will simply run out of power. You see, both Voyager 1 and Voyager 2 are powered by RTGs, radioisotope thermoelectric generators. These are small, reliable power sources that convert the heat from decaying plutonium-238 into electricity. It's not a lot, just a few hundred watts, about enough to power a light bulb or a coffee maker, but it's been enough to keep the Voyagers alive for nearly 50 years. Every year, though, the output drops a little. As the plutonium decays and the thermocouples wear out, there's just not enough energy to keep everything running. So engineers have had to make sacrifices, shutting off instruments, heaters, and backup systems one by one. The spacecraft has slowly gone dim. Voyager 1's cameras were shut down long ago. To save power, yes, but also because, well, there's nothing to see out there, just blackness. Still, it continued to send us magnetic field data, plasma readings, and cosmic ray measurements. Tiny bits of science from a place no human had ever reached. Until, in 2023, Voyager 1 suffered a strange fault. Its data started coming through as gibberish. Engineers on Earth spent months deciphering the problem. Think of it. Scientists trying to repair a computer older than most of their lab equipment, over 24 billion kilometers away, using only coded pulses of radio commands that take 22 hours to arrive. But they fixed it. It was one of the most extraordinary long-distance repairs in history, a testament to human cleverness. But it was also a reminder, Voyager is fragile, it is old, it is tired, and time is running out. By 2025, possibly sooner, NASA expects that the last of the scientific instruments will be shut down. The Voyagers may still be able to send a carrier signal, a sort of heartbeat, but without data, without a voice. Eventually, even that will go silent. And then, nothing. No beep, no signal, no confirmation that it's still there, just a void. And yet, somehow, it's not sad, because what a journey it's been. Launched in 1977, they flew past Jupiter, taking the first close-up images of its turbulent storms, its icy moons, its faint rings. They passed Saturn, revealing the astonishing detail of its ring system and discovering new moons. Voyager 2 alone went on to visit Uranus and Neptune, still the only spacecraft ever to do so. They gave us our first real glimpse of the outer solar system, its majesty, its strangeness, its surprises. They changed textbooks. They inspired generations of scientists. They reminded everyone that Earth is a blue dot in a vast cosmic ocean. And they kept going, out of the sun's protective bubble, into the interstellar wind, sending whispers from the edge. For decades, they survived solar storms, cosmic rays, deep cold, memory glitches, and the slow fade of power. But when they fall silent, they won't die. They'll just continue, coasting without engines, driven only by momentum, away from the sun, forever. And here's the part that moves people the most. Even when we can no longer hear them, they will still be listening. Both Voyagers will continue to carry their golden records, still sealed in their cases, still engraved with their maps, still containing greetings in 55 languages, photos of life on Earth, mathematical instructions, and a message from the then UN Secretary General that reads, "We step out of our solar system into the universe, seeking only peace and friendship." Think about that. The moment we become truly deaf to Voyager, when no more signal comes through, that's not the end of its story. It's the beginning of its legend. It becomes a time capsule, a messenger, a relic, a ghost ship built by Earthlings, sailing a galactic sea. And if one day someone finds it, they'll know that a civilization once lived here, that we weren't just war and pollution and division, that we had curiosity, that we made art, that we laughed, that we dreamed, that we reached out. And even if no one ever finds them, even if the Voyagers wander in total darkness forever, we will have still done something magnificent. We will have sent a piece of ourselves beyond the stars, and the silence that follows, it will not be emptiness, it will be echo of everything we were brave enough to send into the unknown. So, when Voyager goes quiet, know this: it doesn't mean it's lost. It means it's free. The road ahead, how Voyager changed everything. By now, you know that Voyager is far more than a spacecraft. It's a symbol, a trailblazer, a voice in the dark, but it's also something else, a beginning. When Voyager launched in 1977, it didn't just show us the planets. It changed the way we explore. It changed the way we think about time, distance, and even ourselves. And its impact is still echoing. Let's talk about what Voyager gave birth to, a new kind of exploration. Before Voyager, our space missions were cautious, short trips, small hops. Just reaching orbit or the moon felt like magic. Voyager dared to leap far beyond. It was the first mission to aim for the outer planets in one grand sweep, thanks to a rare planetary alignment that only happens every 176 years. Voyager used gravity assists, slingshotting from planet to planet, picking up speed, dancing through the solar system like a stone skipping across water. That technique, it's now a standard tool in deep space navigation. Almost every long-distance probe, Galileo, Cassini, New Horizons, borrowed from Voyager's playbook. Voyager made bold thinking normal, the birth of the Deep Space Network. To talk with Voyager, NASA had to build something just as incredible, the Deep Space Network, DSN. It's a global system of massive radio antennas in California, Spain, and Australia. These dishes are so sensitive they can pick up Voyager's signal, a whisper a billionth of a watt, like hearing a snowflake fall on a pillow, from across the ocean. Without the DSN, we wouldn't hear anything. But because of Voyager, this global ear exists. And now it listens to every mission beyond Earth orbit. It's how we talk to Mars rovers, to Saturn probes, to asteroid explorers. It all started with the need to stay in touch with a spacecraft heading for forever. New missions, same spirit. Voyager also inspired a new generation of explorers. Think of New Horizons, launched in 2006, on its way to Pluto and beyond. It was often called Voyager's child, and sure enough, when it passed Pluto in 2015, it sent back breathtaking images of icy mountains, hazy skies, and a frozen heart-shaped plain. Pluto went from a blurry dot to a living world. Why? Because Voyager proved it was possible. Because Voyager showed the value of patience, boldness, and curiosity. And today, the Interstellar Probe mission is on the drawing board, a next-generation Voyager. It would be faster, better instrumented, and designed to sail 1,000 astronomical units from the Sun, 10 times farther than Voyager ever will. a changed perspective. And then there's the emotional legacy, because Voyager didn't just send back photos, it gave us a mirror. Remember the pale blue dot? That single photo, taken in 1990, when Voyager 1 was already 6 billion kilometers from Earth, at Carl Sagan's request. Earth was just a speck, a pixel, floating in a sunbeam. But it changed how people thought about our planet. No borders, no wars, no politics. Just a tiny world, shared by everyone, fragile and alone in the vastness of space. It humbled us, and it united us. It told us that we belong to the cosmos, not as rulers, but as a part of something vast, ancient, and beautiful. Voyager helped shift our sense of identity from national to planetary to cosmic. The legacy we leave. Voyager also planted the idea that we should send messages to the stars. The golden records were bold, an act of cosmic optimism. We didn't know who would find them. We didn't know if anyone would, but we sent them anyway. That tradition has continued. The pioneer plaques came before. The Arecibo message was beamed afterward. The Rosetta spacecraft carried images of Earth's languages. The Artemis missions now plan to store knowledge on the moon. Voyager showed us that what we send into space matters. It isn't just science, it's a statement. We are here, we're learning, and we care about connection. A universe of Voyagers. But perhaps the most beautiful part of Voyager's story is how it changed people. Engineers who worked on it say it was the proudest moment of their careers. Scientists called it the mission that gave us a cosmic perspective. And ordinary people, artists, children, poets, found themselves dreaming more boldly because of it. Voyager didn't just explore space, it opened it. It cracked open the heavens and said, "You are invited." And long after the signals fade, that invitation remains. And you, too. You may not have been alive when Voyager launched, but its story belongs to you. Because Voyager is still flying, still carrying our atoms, our voices, our music, and our dreams. It's carrying you in a way. Everything Voyager represents, curiosity, courage, imagination, is inside you too. And whether you become a scientist, a teacher, an artist, or simply someone who wonders about the stars on a quiet night, you're continuing its legacy. Voyager reminded us of something profound. The greatest journeys don't always end. Sometimes they just keep going. When the signal stops, Voyager's final whisper. You've followed Voyager on its incredible journey, through the solar system, across the heliopause, and into the dark reaches of interstellar space. You've felt the tension of its discoveries, the wonder of its records, the legacy it leaves behind. But now, as we reach the final chapter of Voyager's tale, we must talk about something delicate, something inevitable. What happens when the signal stops? A fading voice. Right now, Voyager 1 and Voyager 2 are both still alive. They're old, but functioning, barely. Each year their power drops. Each year, engineers at NASA make tough decisions. Which instrument do we turn off next? Which heater must go cold? You see, Voyager is powered by a tiny nuclear battery, a radioisotope thermoelectric generator, RTG. It converts heat from decaying plutonium into electricity. But that heat is fading, and by the early 2030s, there just won't be enough left to keep even a single instrument alive. The spacecraft won't crash. It won't explode. It will simply go quiet, like a lantern that's burned down to its last ember. One day, it will send its final data, one last ping across the void, and then silence, a still beating heart. But even in silence, Voyager will not die. It will keep flying, coasting on forever, past star systems, through nebulae, beyond the spiral arms of the Milky Way. Voyager 1 is heading toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. Voyager 2 is bound for Ross 248, another distant sun. No one will hear them, but they will still be there, ambassadors in motion, carrying the golden record, spinning quietly like a message in a bottle on an endless cosmic sea. The records will survive for at least 1 billion years, maybe longer, long after Earth is gone, long after the mountains erode and the seas boil away. Voyager will still be out there, bearing witness. No tombstone required. Some say it's sad that Voyager will die alone, unvisited, drifting in cold silence. But think about it differently. Voyager has already done more than any spacecraft in history. It's seen worlds no human has ever touched. It's taken the most famous photograph in human history. It's traveled farther than any object we've ever built. It's brought humanity to the doorstep of the stars. And even when its signal fades, its legacy will not. Its discoveries have already changed science forever. Its courage has already inspired millions. Its quiet endurance will continue to echo in everything we send beyond Earth. The last message. At NASA, they joke, half seriously, that one day Voyager will stop talking, and they'll miss it like a friend who's moved away. They'll check the screens one day. No new data. They'll send a final command. No response. And in that moment, something ancient will settle. We'll know that, somewhere out there, 2 spacecraft are still flying. Not gone. Just out of reach. Still Voyager. Still voyaging. You are part of it. And here you are, sitting in your room, in this moment, learning about this ship, its story, and its meaning. That's how the story continues. Not in circuits, not in signals, but in you, in your curiosity, in your wonder, in your imagination. Because even though Voyager's voice will fall silent, it's already spoken to the future, and the future is listening. Close your eyes and drift with Voyager. Now, take a slow, deep breath. Let your body settle. Let your thoughts quiet down, just like the stars outside Voyager's window, still, ancient, and glowing in the dark. Picture yourself aboard that little spacecraft. No engines rumbling, no crowds, just the soft hum of silence and the endless stretch of space all around you. Imagine looking out. You see nothing and everything. 1,000 stars like tiny lanterns flickering in the black. Behind you is home, our pale blue dot, now so far away it's smaller than a speck. But you're not afraid. You're calm, peaceful. Voyager has no destination. It just moves forward, slowly, gently, always exploring. And so do you. Your journey isn't about rushing. It's about noticing, feeling, dreaming. Feel the quiet rhythm of your breath, in and out, like solar wind brushing against a silver wing. You are floating, not just through space, but through time. Every second that passes is part of a story that began before you were born and will continue long after. You are part of something bigger, something beautiful. And just like Voyager, you don't need to understand every star. You only need to be curious, to keep going, to keep wondering. Let your thoughts drift. Let them slow. Let your body rest. You are safe. You are stardust. And you are never really alone, because Voyager is still out there, whispering on your behalf. Good night, explorer. Sleep well.